Hello, my name is Arki and welcome to the physics lab of Foucault Education Project. Tonight I'm going to be talking about heat transfer in liquid nitrogen, and here in front of me I got a thermos filled with liquid nitrogen, and by the end of this video you will understand why exactly I can do this without getting a severe frostbite. Also in front of me I have some other experimental materials and apparatus. I got a styrofoam tray and an aluminum disc with a thermocouple, a temperature sensor, embedded into its wall. Also, I got another thermocouple attached to the wall of this tray. And these two thermocouples, they are connected such as they're working against each other. So the plus of one thermocouple is connected to the plus of another thermocouple, and those two minuses of this total big thermocouple, which is called the differential thermocouple, are connected to the voltmeter, or in my case specifically is a data acquisition device connected to my computer, so I can log data and display it on my screen. So now I'm going to fill the tray with liquid nitrogen, and this sensor will be exposed to the temperature of liquid nitrogen. All right, nice and full, and I'm going to start the data acquisition device. And we see now we are reading something around 14 degrees Celsius, maybe not as accurate because the temperature difference between liquid nitrogen, which is at minus 196 degrees Celsius, and the room temperature, which is approximately probably 22-25 degrees at the moment, is so big that the lookup table or the calibration polynomial I'm using in my software to convert electrical signal back into the temperature maybe not works as well as we might expect, but the closer the temperature of this measurement thermocouple is going to be approach the temperature of liquid nitrogen, the better the precision is going to be. So what I'm going to do, I'm going to quickly lower this disk into the liquid nitrogen, and we'll see what's happening with its temperature. And temperature begins to go down, goes down, and keeps going down. But interestingly, it's not as fast as one might imagine, and I'm going to try to zoom in so you can better see what is going on with the surface of the disk inside of the tray. As you can see here, the disk is covered by a relatively small number of really large bubbles. I mean, it's still a pretty big number, but the bubbles are really big. I can tell their size is between probably 5 and 10 millimeters, and they're very big. And the temperature is going down really, really slow and smooth. I don't know, it's probably already 30 seconds, and it's still only at minus 111, 115 degrees Celsius. Not impressive. So nothing what I would expect from like a super cold fluid, like especially what you see in movies when things are freeze instantaneously. But let's see what's going to happen when the temperature goes down a little bit further. And please pay attention to what's happening to the surface of the disk. And we are really close. And now something else happening. And very quick, the temperature drops, and you could see that this mode of boiling, when we had relatively small number of really large bubbles, has sort of really instantaneously or very close to that changed to like almost like explosive phenomenon when a lot of small bubbles really fast changing, and it was like almost like an explosion. So something has changed qualitatively here. And at that very moment, the curve, the temperature has dropped really fast, and everything was over in a matter of a few seconds. So before we started, the temperature was going down all the way from room temperature down to approximately minus 150 or 160, 170 degrees Celsius, very, very slowly and gradually. But then something has changed, and we could see it on the video. And the heat transfer has intensified so much that things are like the cooling process has ended in a matter of seconds, really fast. And this, what you've seen now, is called a bubble boiling transition, or film boiling to bubble boiling transition. So essentially, when the surface of this aluminium is too hot for the fluid to touch it efficiently, it actually forms those really large bubbles, all those pockets of nitrogen gas, evaporate nitrogen gas, and they essentially insulate the surface rather efficiently, and they prevent really efficient heat transfer. And this goes on for a pretty long time, and the temperature is still going down because there's still some non-zero heat transfer coefficient, not entirely insulated. And then as the temperature goes down and this much more efficient and intensive bubble boiling regime can exist, then there's transition occurs, and once the transition occurs, the heat transfer coefficient increases like 1 to probably 2 orders of magnitude, or 1.5 orders of magnitude to be precise. And that means that the amount of energy removed from the disk per unit time increases that proportional to that amount of time. And now I'm going to show you the presentation I have prepared. And we'll see what the data I used to make this demonstration. And here on this slide, you can see the Cape-type differential thermocouple response as the function of temperature, voltage, temperature. So this allowed me to convert the output of this differential thermocouple into the difference, the wall difference. It's also called a superheat, the difference between liquid nitrogen and the temperature of the aluminum. And another data that was really critical to implement this experiment, and especially in order to process the experimental data I was obtaining, is the heat capacity of aluminium. And what you can see here, that aluminium heat capacity strongly depends on temperature and drops quite significantly when we go down from room temperature to 77 Kelvin, which is the boiling temperature, or minus 196 degrees centigrade. So the boiling temperature of liquid nitrogen, that's approximately 3 times or so. And this is what distinguishes the normal heat engineering, normal heat transfer at like high room temperatures from heat transfer at low temperatures, because heat capacity of materials tends to go down significantly when temperatures go down to the cryogenic levels. And at liquid nitrogen is still not that bad, but if you go further down, closer to liquid helium, then essentially the heat capacity tends to approach zero. And that means that in order to reduce the temperature of a material that has low heat capacity, it takes much less energy to extract from it to reduce its temperature by 1 degree or 1 Kelvin. So, and now finally, I applied all this knowledge and a little bit of smart, clever thermodynamics, and I managed to convert all this temperature data into heat transfer coefficient versus wall superheat. And this is pretty cool, pun intended, because now here we can see two very distinct regions. And the one is red, of course, data points are scattered all over the place. It's a very simple experiment, and we just basically cooling, no steady state here, it's all transitional. Still, I managed to derive an average coefficient, which is approximately 370 watts per meter squared Kelvin. I'd say very close to reality. And that's another green region where heat transfer is approximately 5,300 or so average. And you can see that the difference between them is approximately like 220, two dozens or something like that. And this is what's happening. This is why the temperature drops really, really fast whenever the wall superheat reaches approximately 35 degrees or 35 Kelvin. And we can see here, what's also really pleasing here is that the yellow dashed line, because this yellow dashed line, it actually depicts what's called a transitional boiling, or we can also call it partial film boiling, or any other transitional term you can come up with. So this is a mixed boiling. This is where bubble boiling begins to emerge, but film boiling still kind of dominates. And the hotter the surface of the wall is, or the bigger the superheat of the wall is, the more film boiling is there and less bubble boiling there. But then bubble boiling keeps emerging, and as bubble boiling begins to emerge, the temperature of the surface goes down, and that means it actually sort of self-sustaining or encourages more appearance of bubble boiling, encourages more bubble boiling because temperature goes down. And then ultimately we get to make this change of regimes at approximately 22, 23 degrees superheat. So, but very nice to see that such a relatively simple experiment allowed us to even detect and catch transitional boiling, where we have this transition from really big bubbles and poor heat transfer all the way to really big, huge number of tiny bubbles and really good heat transfer. And this is why things are changing so fast. Of course, in reality, if we're talking about physics, things are always more sophisticated and complex than they appear. And of course, here in this region, when the bubble, the wall superheat is below 5, maybe 3 degrees, this is where heat transfer goes down again, because this is where bubble boiling ceases to exist and gives way to natural convection. Actually, this natural convection what finishes off the process of cooling, but because there's very little heat left due to very low heat capacity and really low superheat, it's really hard to catch it within using this kind of experiment. But still, what we managed to determine here is actually two distinct regions where we have poor heat transfer and really good heat transfer, and this is really occurring really fast, this transition. And this is why you see what so you saw what you saw. So like really long, slow bubbling like that, and then suddenly like almost like explosive transition to something like boom, and it's all in a matter of seconds. So it's really satisfying that it is possible to obtain this kind of results, and probably at the end of the day, my PhD in cryogenic heat transfer worth it. And also, in order to demonstrate like it's in a more aggressive and intense way, what I'm going to do, I'm going to pour liquid nitrogen in my palm. And it's basically nothing. It's nothing. I'll just try to probably transfer the liquid nitrogen through my palm back into the thermos. And you see, the reason that I can do it is because the surface of my palm is so hot. It from the point of view of liquid nitrogen, it's basically red hot, and it can't touch it. So once it approaches close enough, then it begins to suddenly evaporate, and it forms this cushion of vapor, which has really poor heat, allows for really poor heat conduction or heat conductivity. And there's no much heat transfer, so it's basically just my palm repels it and it can't really touch it. Of course, if I just hold it for long enough in liquid nitrogen, allowing the temperature of the surface of my skin to go down, then things go bad really fast. And I just want to warn you that just don't try to do this unless you are trained or supervised by a trained specialist, because I'm trained, have experience about more than 20 years working with liquid nitrogen, and with liquid nitrogen things are all fun and games until things go south. So please be very careful, and if you're not trained, don't try to repeat it at home. And please let me know if you want to know a little more about the theory of boiling and heat transfer, and also probably the most interesting part, the experimental methods I used in order to obtain this data and convert the data from electrical signal all the way to temperature, all the way to heat transfer coefficients. Thank you very much for your attention, and I see you next time. Bye.